Hello, hello. Good morning, friends. Good morning, students. Department of Collegiate and Technical Education, Bangalore. Automobile Engineering Department, that is 5th semester subject Design of Machine Elements. So here in this subject, that is unit number 5, Design of IC Engine Parts. So here in last session, I covered the design procedure of the piston, detailed parts of the piston and detailed procedure of the piston. So that I have taught in last session. Okay, so now in this session actually I will do the problems. Okay, so next here actually contents. What are the contents are here? Let us understand. So first one is simple problem. In this session, contents are here: simple problem, multiple choice questions, and references. These are all the contents which are included in this session. Okay. So here, this is the actual problem. So what is the actual problem here? So let us understand. So first I will read the question. Design a cast iron piston for a single acting 4-stroke engine for the following data. Cylinder bore 100 mm, that is capital D is given. Stroke length, that is capital L is given, that is 125 mm. Maximum gas pressure, so that is equal to 5 Newton per mm square. Indicated mean effective pressure 0.75 Newton per mm square. Mechanical efficiency is also given in the problem, that is 80%. Fuel consumption 0.15 kg per brake power hour. Calorific value is given, that is 42 into 103 kilojoules, that is not 103, 42 into 10 raised to 3 kilojoules per kg. Speed is 2000 rpm. Okay, assume that permissible stress for cast iron, that is 38 Newton per mm square. Permissible stress for piston ring, that is equal to 100 Newton per mm square. Cylinder wall pressure is given, that is 0.035 Newton per mm square. Permissible bearing pressure on piston barrel, that is equal to 0.45 Newton per mm square. Permissible bearing pressure for piston pin, so that is equal to 25 Newton per mm square. So this is the actual problem history. So given data, so that I have taken D is equal to 100 mm, that is diameter of the piston. Capital D is equal to 100 mm, then stroke length is equal to 125 mm, then P is equal to 5 Newton per mm square, then mean effective pressure, that is P suffix P, that is 0.75 Newton per mm square, and H mechanical efficiency is equal to 80%, that is 0.8, and mass M is equal to 0.15 kg per pp kilowatt hour. HCV higher calorific value, that is equal to 42 into 10 raised to 3 kilojoules per kg. Okay, so here N is equal to 2000 rpm, that is 2000 rpm, but I am going to convert it into rps. So that is 2000 divided by 60, but wrongly it is printed, that is divided by 30. So instead of 30, you make it a correction, 2000 divided by 60, that is 33.33 rps. So here this one is the superflows data. So where the star mark is there, so that is called as superflows data. So that will not be applicable anywhere. So L is not going to be applied, and M is not going to be applied, H is mechanical efficiency is not going to be applied, mean effective pressure and HCV. These are all the extra data which are given in the problem. Okay, so next sigma is equal to 38 Newton per mm square for cast iron. For piston ring, 100 is equal to 100 Newton per mm square, and PR is equal to 0.035 Newton per mm square. PB bearing pressure is equal to 0.45 Newton per mm square for piston barrel. Okay, PB bearing pressure for piston pin, so that is different, that is equal to 25 Newton per mm square. The dimensions for various components of the piston are determined as below. Okay, so now, what are the steps or here what are the important steps so that should be considered while designing the piston? Tell me. So first one is we have to design about the piston head or crown. So on the basis of heat dissipation and on the basis of strength, we have to find out the T1 value. That is T1 is nothing but thickness of the piston head. Okay, so it means first step is piston head, design of piston head or crown. After that we have to design about the piston rings. So after that we have to design about the piston barrel. After that we have to design about the ribs, and after that we have to design about the piston pin. So these are all the procedure steps. Okay, so first one is the piston head design or crown. So first one, thickness of the piston head on the basis of strength. So first thing is on the basis of piston, on the basis of strength only we are going to find out T1 value. So T1 is equal to, this is the standard formula, T1 is equal to 0.43D into bracket into square root of small p divided by sigma d. Therefore 0.43 into 100, because it is d value, into square root of 5, that is p value, divided by 38. 38 is nothing but the stress, that is 38 Newton per mm square. So by simplifying it, we will have this value, that is 15.59. It can be rounded about to next two digit, that is 16 mm. The thickness of the piston head on the basis of heat dissipation. So but here first answer is on the basis of strength. So on the basis of strength only we got this value. So now we are going to calculate the T1 on the basis of heat dissipation. Just now we can apply the now we will apply the formula, that is T1, that is on the basis of heat dissipation. So T1 is equal to d square, capital D square into Q divided by 1600 into capital K into bracket T suffix C minus T suffix E. So this relation or this formula is available in page number 409 in DDHB, that is Design Data Handbook. Okay, so here Q value is not given in the problem. So at that time Q can be taken from the DDHB, that is standard, which is given in the problem. Okay, so here this is the cast iron piston. For the cast iron piston, so the ranging Q is equal to this much. Okay, so therefore K is equal to 460 joules per second meter square into degree centigrade. It means degree centigrade per mm. So TC means T. So it is also given, or sometimes if it is not given in the problem, so that has to be assumed, that is T suffix C minus T suffix E, that is equal to 220 into, that is common factor or common data which has to be taken. Okay, degree centigrade. Okay, after that, so after finding the T1 value on the basis of heat dissipation, so actually we have two values, that is T1 on the basis of strength, that is 16 mm, and T1 on the basis of heat dissipation, that is 4.81. Okay, so now we are having these two values, but higher value should be taken into consideration. That is higher value among these two, T1 is equal to 16 mm is the highest value. So therefore T1 is equal to 16 mm. Thickness of the piston head is equal to 16 mm. It should be adopted. Okay, so next LS. So it means LS. So LS is equal to, ratio is given. So LS means length, stroke length, that is 125 mm, and diameter of the piston, that is 100 mm. So that is equal to 1.25. Therefore, a cup in top of the piston head with a radius equal to 0.7 D, that is 70 mm, is provided. So now radial ribs. Okay, so design of ribs, that is piston rings and ribs. So radial ribs may be 4 in numbers. Okay, the thickness of the ribs varies from this range. Okay, therefore thickness of the ribs T6 divided by 3 to 16 by 3 to 16 by 2. Okay, so therefore TR is equal to 5.33 to 8 mm. So now let us adopt 7 mm. So this is the thickness of the radial ribs. Okay, so next piston rings. So design of piston rings. So design of piston rings, that is the third step. The radial thickness of the piston ring, TR is equal to D into square root of 3PR upon sigma. So this is also one type of equation which is available in DDHB, that is Design Data Handbook. equation number 18.17a, wide page number 411. Therefore, TR is equal to, that is thickness of the radial thickness of the piston ring. TR is equal to 100 because D value 100. So square root of 3 into 0.035 upon 100. So by simplifying it, you will get this value, that is TR value, that is 3.24. Then the axial thickness or depth of the piston ring. So that is small h is going to be found out, that is 0.7 times of TR to 1 TR. Therefore, 0.7 into 3.24 to 3.24. So finally you will get a 2.26 to 3.24 mm. Okay, now let us adopt h is equal to 3 mm. So we also know the minimum depth of the piston ring. Okay, so next step is h. Small h is equal to capital D divided by 10 into I. So here I is nothing but number is, that is 4 number. Okay, number of grooves, I think. So therefore 100 divided by 10 into 4. So taking I is equal to 4, therefore assuming I is equal to 4, therefore 4 is added here or 4 is substituted here. So by simplifying it, you will get h value, that is 2.5 mm. Thus the depth of the piston ring as already calculated, that is h is equal to 3 mm, is satisfactory. So here so first thing is we have calculated h value, that is 3 point something, but here h is equal to 2.5. So higher value is going to be considered. Therefore h 3 mm, h is equal to 3 mm, this is satisfactory value. So the distance from the top to the first groove, distance from the top of the piston to the first groove of the piston ring, so that is Tg is equal to T1. T1, so range is like this, Tg is equal to T1 to 1.2 times of T1. So therefore 16 to 1.2 into 16, therefore 16 to 19.2 mm. Now let us adopt Tg is equal to 17.6. Okay, so the lengths between the ring grooves can be given by. So next step is T land is equal to h, so that is equal to 3 mm. Okay, so next piston barrel. So next fourth point is design of piston barrel. So piston barrel, so here in this we have to find out the thickness of the piston barrel. The equation is like this, T3 is equal to 0.03 D plus B plus 4.5 mm. This equation is readily available in Design Data Handbook, that is page number 410. So after substituting all values here in this equation, 0.03 into D plus B means TR plus 0.4 mm, because B value plus 4.5 mm. So by simplifying it, you will get this value, that is T3 is equal to 11.14 mm. So next thing is the wall thickness towards the open end of the piston. So that is T4. Okay, so you have calculated a T1 value, T2 value, T3 value. Finally, you have to find out T4 value, that is wall thickness towards the open end of the piston. So T4 is equal to empirical formula, which is available in DDHB, page number 410. T4 is equal to 0.25 times of T3. Therefore, that is equal to 0.25 into T3 means 11.14. So like this, you will get 2.785 to 3.8999. So now let us adopt T4 is equal to 3.34 or 3.4 mm. It is adopted. Okay, next coming to discuss about the next procedure, that is piston, design of piston skirt. But here in this design, maximum side thrust on the cylinder due to the gas pressure. So R is equal to, what is the equation here? R is equal to 0.1 into area into P. So therefore 0.1 into area, that is pi divided by 4 into D. D means the diameter of the piston, that is 100 square, into P, that is pressure. Okay, by simplifying it, you will get one value, that is R. R value we got, so 3926.99 Newton. So now you can call it as equation number 1. Now side thrust due to bearing pressure on the piston barrel. One more equation is here, that is to find out R value, that is capital R is equal to PB into capital D into small l. Therefore PB means bearing pressure on the piston barrel, that is 0.45 into 100, that is because it is D value into small l. Therefore 45 L 45 into L. So R is equal to 45 into L in terms of Newton. So now you can call it as equation number 2. So now equating the equations 1 and 2 we have. So what is the equation number 1 here? So 3926.33. So put it on this side. That is equal to right side you can keep the second equation, that is 45 into L. Therefore among these two equations L is the unknown here. So take it as outside. Therefore L is equal to this much divided by 45. So finally you will get the length of the skirt, that is L. So L is equal to 87.26. So now we can make it as round figure, that is 90 mm. So like this it completes. It is not completed. One more point is remember, one more point is pending here, that is length of the piston L. So capital L. So actually here before that you have calculated small l. Small l is nothing but length of the piston skirt, but here length of the piston, that is capital L. So L is equal to capital D to 1.5 times of capital D. So D is known thing, that is the diameter of the piston, that is 100 mm, which is given in the problem. So 100 to 1.5 times of D value. So therefore 100 to 150 mm. So now let us adapt, because 100 is here, 150 is here. So mean value L is equal to 125, because 100 plus 150 divided by 2 you will get 125. So this is the mean value for these values. Therefore now let us adapt L is equal to 125 mm. So next thing is last step, that is piston pin, design of piston pin. So here in this design, length of the gudgeon pin bearing, that is L1. So L is different, L1 is different, capital L is different. So don't get any confusion here. So small l is different, capital L is different. Small l is nothing but length of the skirt, capital L is nothing but length of the piston, but small L1 is nothing but length of the gudgeon pin bearing. Okay. So gudgeon pin bearing is also called as gudgeon pin bush. Okay. So L1 is equal to 0.45 times of D, 2.5 times of D. So this equation is readily available in design.our handbook, page number 411. So therefore by applying all these values in this equation, that is L1 is equal to 0.45 into D, D means 100 to 0.5 to 100, 0.5 into 100. Therefore you will get this value 45 to 50 mm. Okay. So therefore you can take average value for these two, that is 45 and 50. So you will get L1 is equal to 47.5 mm. So therefore now the diameter of the piston pin. Okay. So now we have calculated L1 value. So we have calculated small l value and capital L value and small L1 value. Okay. So finally you can calculate the diameter of the piston pin. So what do you mean by piston pin? It is nothing but gudgeon pin. Gudgeon pin is going to be used for connecting the small end of the connecting rod and piston assembly. Therefore D should be calculated, that is diameter of the piston pin is going to be calculated here. So what is the equation here? Equation is already available in DDHP, that is design data handbook, that is page number 411. That is small d is equal to pi into capital D square. Capital D means what? Piston diameter. Okay, into maximum pressure, P maximum, divided by 4 times of L1. So L1 is different. What do you mean by L1 here? So L1 means what? Length of gudgeon pin. So that you have already calculated here, into PB, bearing pressure. So by applying this formula and by substituting the all values in this equation, you will get D value. Okay. So next, so this is the actual procedure of the piston design. So these are all the parameters of, these are all the steps. These are very important to make a design of the piston. So now last topic is multiple choice questions. So here there are so many questions are here. So first question is like this: the thickness of the piston head on the basis of strength T1 is equal to 0.43 D when D is equal to 100 mm and P is equal to 5 Newton per mm square, then T1. So T1 is to be calculated by using the equation after finding out and after substituting all the values in the equation. Finally you will get a T1 value. So this right answer is A is the right answer. That is 15.59 is the right answer for the question number 1. Okay. So next, the second question is temperature at center of the piston TC and edge TE for the cast iron piston is dash. So TC minus TE. So range is given. The standard range is 222 degrees centigrade. So here, among these 111, 222, 333 and 444, and right answer is the B answer, that is 222 degree centigrade. So next coming to discuss about the third question, that is temperature at the center of the piston TC and edge for the aluminum piston is. So same question, I think it may be repeated, but for the aluminum it is also same thing, that is 222 is the right answer. That is no, don't confuse them. But actually, cast iron piston is 222. But the piston temperature at the center of the piston TC and the edge of the TE for the aluminum piston is different, quite different. For the cast iron piston, it is around about 222 degrees Celsius. But here, this one is the special piston, that is aluminum piston. So here, for this question, the right answer is 111. E is the right answer for the question number 3. So next, question number 4, that is radial ribs for the piston. TR is equal to T1 by 32, T1 by 2, and T1 is equal to 16 mm. Then TR is like this. So we have to judge the answer for this question. That is question number 4. I think A is the right answer. That is 5.33 to 8 mm after calculating and substituting the values in this empirical formula. Okay. So next, question number 5. Radial thickness of the piston ring. TR is equal to D and D is equal to 100 mm. PR is equal to 0.035 Newton per mm square. That is equal to 100 Newton per mm square. Then TR is equal to what? Okay. So by applying the formula, and finally you will get the answer. Okay. So for the question number 5, so right answer is C answer, that is 3.14. So next, question number 6, piston barrel T3, that is equal to 0.03D plus B plus 4.5 mm. When D is equal to 100 mm, TR is equal to 3.24 B. So here then T3 is equal to, so for the T3 answer, that is D is the right answer. It may be a right answer, that is D is the right answer for question number 6, that is 11.14. The last two questions are made here. That is 7th question is length of the piston, piston L is equal to D to 1.5D, where D is equal to 100 mm, L is what? Okay. So for 7th question, C is the right answer, that is 125 mm is the right answer for question number 7. So next, last question is piston pin. So that is L1. So L1 is equal to 0.45 times of D to 0.5 times of D. When D is equal to 100 mm and L1 is equal to like this. So these are all the answers. But right answer is A is the right answer, that is 45 to 50 mm. So 8 questions are here and all answers are shown in this slide. Okay, so get the benefit. First, don't see the answers. First, you read the question and understand the concept and judge the answer. Later on, you can see the answers listed. So that I have listed here. Okay. So this is the procedure of the doing the actual problem. So what are the given data, so that you have to understand clearly. Then you can start up the actual procedure of the piston. So for making this video and for preparing this video presentation, I have referred so many books like R.S. Kurmi, Billari, and along with these two books, I have referred one more book, that is DDHB Design Data Handbook, written by K. Mahadevan and K. Balveer Reddy. Okay, so finally, I am very thankful to our LMS team, so our chairman Gopinath sir, and I am very thankful to LMS coordinator Jagdish Pogli, Anil Logre, and our subject moderator sir T.P. Chavan sir, and my sincere thanks to our subject expert Mr. S.S. Shamboji, who is selection grade lecturer in KHK Polytechnic, Harvard. Okay, so finally, once again, I am thankful to other content developers like Shanapapurad and Shanapasapavit and MKP Vyade, Vinayak Nayak, as well as Nayak SP, and so many faculty are there to make a content or for developing this e-content. Okay, so I am very thankful to all my colleagues. So for any queries, please mail to this ID, that is bhwmascmkrl@gmail.com, bhwmascmkrl@gmail.com. Okay, thanks for watching my video presentation. Okay, thank you one and all. Thank you.